Episode 14, Design, Hydronics, Liquid Radiant Floor Heat. I chose to use hydronics, in-floor heat, to heat my house. In order to do this, you need to know several items. First, you need to know how much heat you will need. To do this, we chose the coldest day of winter. For northern Minnesota, I used 18 below Fahrenheit. Find the heat loss out of each room. This allows you to design a hydronic circuit for each room. Add the rooms together to get the total heat loss for your house. This will be the size of the boiler that you need. Hydronics uses fluid dynamics. I took this course junior year of college as an aeronautical engineer. We need to design and balance turbulence, the Reynolds number, head loss, which is drag, resistance to flow, and heat transfer. There is some great software out there to assist you in your design. I used and recommend loopcad.com. This is a program that you download to your computer and then design your system. It is wonderful. There's some great software out there to assist you with your design. I used and recommend loopcad.com. This is a program that you download to your computer and then you design your system. It is wonderful. Avenir puts a product out. You go online to Avenir Online or loopcad.com and then you download the program into your computer. I used LoopCAD 2020. They've upgraded it. Now we're up to 2024. As you come down here, what the program will do for you, and I'll show you this a little bit later, is you go ahead and you draw your floor plan in to include the types of windows, the doors, insulation value of your walls. It will automate in a circuit drawing in there once it calculates heat loss out of that based on where you are, the outside temperature and your heat requirement. Gets all these heat loss calculations done, cooling calculations if you need them. It'll do your your hydronic calculations to figure out the inputs in each circuit, how much heat you're going to place and what your manifold requirements are. Snow melt if you need it for a driveway. And you've got some great 3D CAD views that they give you at the end. And it's just a great program. If you're going to do a project like this, you need something like LoopCAD. After you have downloaded the LoopCAD program, you can then begin to design your system. Here's just a quick overview of some of the items in the program. First, over here under Floor Plans, you draw your floor plan to include your windows, the insulation R value, other items from your floor. From this, the program will be able to calculate the heat requirements for each room. If you come down here to the Floor Plan Properties, under the General tab, you can see the characteristics of the floor defined, including the type of floor, wall height and thickness, joist spacing, among other items. If you go to the Load Summary tab, you can now see the room volume area, the heat loss from each of the items on that level. You can see here that my heat loss for this floor is 13,302 BTUs per hour total. Get some recovered, my net heat loss 11,481 BTUs per hour. Closing that, moving to the Circuits tab, looking down in the basement. You can then draw circuits in each of the rooms to meet the heat requirements of each room. Here are my circuits for the basement. And you do the same for the main floor, and the same thing for the upstairs for the second floor, with each one of the circuits outlined here with the heat that they will provide. Moving to the Materials tab, the program automatically calculates what items you may need for your project. These are recommendations. You can see it includes tubings, manifolds and fittings, tools, accessories, and control valves. It even gives you pictures of your item, both down at the bottom and if you hover over the items themselves. You'll notice that under tubing, it properly specifies O2 barrier pipe. Remember that oxygen barrier tubing is required for hydronics, but is prohibited in potable water applications. Finally, moving to the Reports tab and the drawing, you get great information about the project that you've put together. Here's my basement, moving to my main floor, moving to the upstairs, much of the information out of the earlier tabs. Last, the program under Reports Coil Schedule even gives you a cut schedule for your rolls of oxygen barrier PEX so that you don't come up short by cutting the wrong lengths from the wrong coils. And you can see that here under the circuit cut schedule, which coils and how many feet to take off of each coil as you come across. Also, as we move down the left to the heat loss summary, you noticed here that for the total for the project, we have a design load, total heating load of 85,986 BTUs per hour. So when I get a boiler, I need to have a boiler that exceeds that requirement. Now we are going to get a little bit technical into the weeds on the hydronic design. Some concepts and definitions. Reynolds number, a dimensionless quantity that measures the ratio between inertial and viscous forces. It helps predict fluid flow patterns in different situations. If you don't want heat transfer out of the pipe, like the Alaska pipeline, you need a low Reynolds number. At low Reynolds numbers, the flow tends to be laminar. If you want high heat transfer, hydronics, you want a higher Reynolds number. At high Reynolds number, flows tend to be turbulent. Too much turbulence, though, results in too much resistance, also known as head loss. For proper hydronics, we need to design for a Reynolds number above 2300. Here are depictions of laminar and turbulent flow patterns. You can see how the head loss increases with the turbulent flow. During my design, I needed to balance head loss and Reynolds number. You can see in this circuit chart the columns for each. I'm most interested in the manifold head loss, 11.1 for manifold 1 and 11.2 for manifold 2. Also, you can see when the screenshot was taken that I had not yet gotten a high enough Reynolds number for circuit A-6. It is only at 1,924, which is below the requirement of 2,300. Not enough heat being transferred out of that pipe. Head loss is influenced by flow velocity, pipe length and diameter, friction factor based on the roughness of the pipe, Reynolds number of the flow. Head loss correlates to a piping length that would cause an equivalent head loss. Pumps have only so much ability to move fluid. With increased head loss, the gallons per minute decrease. My system has two manifolds, each with its own pump. Taco 0018E pumps will support these head losses for specific gallons per minute. 0 feet of head loss will give you 16 gallons per minute out of each pump. Increasing the head loss to 6 feet results in a flow of 12 gallons per minute. 10 feet of head loss results in 9 gallons per minute, and 13 feet of head loss results in 8 gallons per minute. Remember, my head loss for my system was about 11. My heat required a total flow of 16.1 gallons per minute, so I went with two pumps at 8 gallons per minute each. Head loss system 1 was 11.1, head loss system 2 was 11.2. This met the specification for the pumps. Here is one of the LoopCAD output reports that we saw earlier. This report is for the main floor, and it gives the requirement and output of each circuit. Each circuit has a load requirement. This is the heat loss that needs to be replaced. The peak number that is listed is how much heat is available from the circuit. My challenge, while controlling head loss and Reynolds number, was to make the peak exceed the load in each circuit. It was quite the iterative task. Some LoopCAD system circuit design considerations. Delta T is the difference between the supply temperature and the return temperature. It is how much energy is transferred out of the fluid during its travel. It is part of the formula used to give a flow rate for the load. What should it be? One installer used a delta T of 20 for baseboards or even 30 for standing iron radiators. He can have it that hot because no one walks on them. Use a delta T of 15 for radiant ceilings and a delta T of 10 to 13 for floors. My design process.
You design first based on the heat load and type of emitter you want, while knowing the acceptable delta T for that emitter. An emitter is the type of tubing, radiator, etc. Now you know the fluid flow needed to deliver the BTUs to the emitter you select. Select pipe size and lengths. Ensure head loss is less than 10 or as close as you can get to this. If head loss is too high, shorten the pipe if excess energy is delivered to the room and/or increase the diameter of the pipe. Ensure the Reynolds number is between 2200 and 4000. This sets fluid velocities at 2 to 4 feet per second to keep the fluid moving along and air moving along to the air removal device, and it minimizes pipe erosion and velocity noise. The maximum circuit lengths from manifold back to manifold are, for 3/8" tube, 200 feet, for half-inch tube, 300 feet, and for 5/8" tube, 400 feet. Manifold boiler design. Modern compact boilers have a much higher flow resistance than earlier cast iron boilers. Because of this, we need hydraulic separation of circuits. The best form of hydraulic separation is closely spaced T's. You can see two closely spaced T's on this image. Hydronic systems use primary-secondary loops for heat transfer. The primary loop is shown here in red. Fluid is heated in the boiler and then circulated clockwise back to the boiler. When it returns to the boiler, heat is added as necessary. The secondary loops are shown going upward on the orange and purple lines. Fluid is taken from the primary loop through the orange line of closely spaced T. These closely spaced T's divert and return fluid as necessary through any circuits that have been opened on a manifold. The returning fluid in the purple line will have cooled and is returned to the primary loop through the closely spaced T. All design elements of the system need to be identified and then designed as I have here. The boiler 1 is on the left. The primary loop goes through the closely spaced T, 16, and the fluid returns to the boiler. When a circuit, 20 or 21, asks for heat, a valve opens, A through Q, and a pump turns on, 19. At this point, some of the heated fluid exits at the top of the closely spaced T, goes through the manifold, heats a room, and returns through the bottom of the closely spaced T. Other design elements present are the red expansion tank, the air extractor, fill valves, and numerous pressure and temperature gauges.